All right, well, hello physics students and welcome to this video lecture that is going to introduce us to angular momentum. So this is a key idea when we start talking about rotational dynamics. We talked about linear dynamics with Newton's laws and linear momentum, but now we're going to start looking at dynamics in terms of rotation. So angular momentum in a nutshell, the definition is pretty similar to our definition for linear momentum. So angular momentum is the quantity of rotation of an object. So to put that a little more simply, so we can understand it a little bit better, essentially the more angular momentum an object has, the harder it is to stop rotating. Okay, so only when an object is rotating does it have angular momentum. Another way that we can look at that is inertia in rotation. So for linear momentum, we said inertia in motion. Here we could just say inertia in rotation. So what I have here, I have two spheres, and they are both rotating about the end of these massless rods. And these rods are the same length, but you notice that those spheres are of different sizes. So obviously this one is much smaller than this guy over here. So our basic moment of inertia equation for something like this is I is equal to mr squared. Well, we know that r is the same for both of these, but this guy has a little itty bitty mass and this guy has a big mass over here. So obviously then this guy has a much larger moment of inertia than this guy. Now let's just say that both of these objects have the same angular velocity, and we use our Greek letter omega for angular velocity. So if both of these have the same angular velocity, but this sphere over here has a greater moment of inertia, well, this sphere then, or this object, is going to have more angular momentum. Now I like to present all of these rotational motion things in terms of things that we already know. So when we think back to linear momentum, we had momentum is equal to mass times velocity. Well, in angular momentum, we're going to have angular momentum is equal to moment of inertia times angular velocity. Now, similarly, when we were studying linear momentum, we had impulse or change in momentum was equal to force times time. Well, in rotational motion, we have a change in angular momentum is equal to torque times time. Okay, so let's just look at the similarities here and the connections that we have between linear motion and rotational motion. Our equivalent for mass in rotational motion is going to be moment of inertia. Okay, that's basically how resistant that object is to rotation. Okay, based on how much mass it has. Obviously, this guy has much more mass, so it's going to be harder to actually get rotating. Our equivalent for velocity is angular velocity in rotational motion. Now, moving on over to impulse here. Our equivalent for force in rotational motion is torque, because torque is a force that causes rotation. And obviously time is the same, okay? So while we're learning a new way to think about motion, we're looking at it in terms of rotation now. Really, all of the equations that we've learned apply here. We just have different symbols. We have different nomenclature, really, for these various things. Now, in terms of concepts here, because both of these have the same angular velocity, and this one has a smaller moment of inertia than this one, well, this guy over here has a much greater angular momentum. Now, we could have equal amounts of momentum if we decreased this angular velocity, okay? Now, to get these things to actually stop moving, okay, for them to stop having angular momentum, we would have to apply a torque over some period of time. Okay, so we would have to apply some amount of force to this object. Let's say we just apply a force here. Well, now that force is being applied over some lever arm distance. Okay, I'll put an L here for lever arm, and that's eventually going to get that thing to stop moving, stop rotating, to be more specific. So it's going to take a much greater torque in the same amount of time to get this guy to stop than it would to get this guy to stop. Now, when I'm saying to get this thing to stop, what I'm actually saying is to cause a change in the angular momentum. Okay, so if we're applying a torque over a certain amount of time to either of these, well, we're going to be changing the angular momentum that those objects have. Okay, so here's your basic intro to angular momentum. While I know that rotational motion can be a little bit tricky, it's really nothing new because we've already learned about all of these concepts in a linear sense, okay, in a translational sense. Now we just have different symbols, different nomenclature that we work with in rotational motion. So tomorrow we're going to delve into those problems a little bit deeper and understand them a little bit more in terms of angular momentum. We're also going to start discussing Newton's second law in a rotational motion context. So have a good night, physics students, and take care.